So I need you to bear with me for a little bit. We're going to take what may seem like kind of a strange diversion here for a little bit, but a couple extras down the road, we're going to tie this back to these antiderivatives or integrals that we've been talking about with what really is one of the highlights of the class. The name just tells you how important it is. It's called the fundamental theorem of calculus. Right? And what we're going to be talking about here is the area under a curve, right? I'd like a way to find out what the area between this curve and the x-axis is. The area in here. A very non-classical geometric shape, right? There's no formula, no geometry formula for the area under a parabola. Right, so what we're going to do first, we're going to do here in this lecture, we're going to talk about ways of approximating the area under a curve. Then as we go along, right, you'll see we're going to come up with a way to take our calculus tools and turn these approximations into an exact value. Okay, so here's how the approximation works. Right, I'm going to take this. What I'm going to do is I'm going to draw a rectangle, right? And I'm going to start with one rectangle, right? N equals 1. And the way I'm going to do this is I'm going to draw my rectangle here on the base because I'm trying to find the area under the curve, between the curve and the x-axis, between -2 and +2. So I'm going to draw one rectangle that approximates this. I'm going to do this using the function value at the midpoint of the interval as the height. Right, so the midpoint of this interval is at x equals 0, and the height is up here. So my approximating rectangle is going to look like this. Right, well, the area of that rectangle, area of a rectangle is length times width. The length at the bottom of my rectangle has a length of 4. And the width, it really looks more like the height here, right? The other dimension is also 4. So I get an area of 16 square units. Now, that's not a very good approximation. All of this area up here and over here is inside the rectangle, so it's part of that 16, but it's not part of the area that I'm looking for. So that would be my error, right? And it's relatively large at this point. So how can I do better? Right? How can I do better? Well, here's what I'm going to do. Let's try doing 2 approximating rectangles instead of 1. All right, so now let's see. I keep calling this n, right? So let's let n, that's going to be the number of rectangles, equal 2. So what I'm going to do is I'm going to take that interval from -2 to 2, and I'm going to divide it into 2 equal pieces. All right, so I'm going to have the interval from -2 up to 0. I'm going to build one rectangle there, and I have the interval from 0 up to +2. I'm going to build another rectangle there. All right, so let's look at that negative interval, the left-hand one first. The midpoint is x equals -1. Right, this is my equation down here, y equals -x squared plus 4. If I go to the height at this point, that's the y value. Right, if I put -1 in there, I get y equals -1 squared plus 4. That's 3. All right, so here's my approximating rectangle. It goes up 3 units over and down. Okay, let's call that A1. Okay, area 1, A for area. Then over on the other side, I'm going to draw a second rectangle. The midpoint of this interval is +1. And if you put +1 into the function, you get y equals 3 again. Right? It makes sense. It's symmetric here. So my second approximating rectangle is going to be here, right? And this height is also going to be 3. So let me call this A2. Okay, so where do we end up then, right? The area of triangle 1, let's see, its height is 3, and its base is 2, plus the second rectangle is the same. Its height is also 3, and the length of its base is also 2. So, whoops, sorry, that's my second rectangle. A1 is 3 times 2. A2 is 3 times 2. Both of them have the same area at 6 square units. The total area, we add those up, and we get 12. So it went down, right? And that kind of makes sense, right? What's my area here? Well, it's this little piece and this little piece, right? I went over by those amounts, but look, I also underestimated because these pieces up here should have been included and weren't. And if you look there, the overage looks a little bigger, right? But it looks like they're going to kind of balance each other out a little bit, so it does feel like I'm getting a better approximation. Okay, so let's try this one more time. And I'm actually going to let you do this. Try doing this with n equals 4. Right, you can pause the presentation here, right? Try to work that out yourself, using the midpoints again. Then start this up and we'll do it together. All right, so let's see what happens. I'm going to take the base there between -2 and 2, and I'm going to divide it into 4 equal pieces. So I'm going to go from -2 to -1, -1 to 0, 0 to +1, and +1 up to 2. All right, so what are my midpoints? Right, well, my midpoints are -1.5, -0.5, +0.5, and +1.5. Those are the halfway points for each of my 4 intervals. So here's what I'm going to do to find my area. Right, I'm going to take each height at those midpoints and multiply it by the width. So what's this going to come out to? Well, it's going to be f of -1.5, that's the left-hand interval, times the length of the interval. Well, the length of the intervals, they're all the same. It's 1. Plus the midpoint of the second interval, that's f of -0.5 times 1, plus interval 3, that's f of 0.5 times 1, plus f of 1.5 times 1. Okay, so what does this come out to? Well, f of -1.5, this is 1.75 times 1 plus 3.75 times 1 plus, and again, we're working the symmetry here a little bit. F of 0.5 and -0.5 are the same. So this is also 3.75. And this is 1.75. If you add all of these up, right, you total these, and you get 11. So you notice what happened, right? Let me make a little table real quick, right? We've got our n values. 1 gave me an area of 16. 2 gave me an area of 12. 3 gave me an area of 11. All right, I want you to have a little flashback here now, right? I want you to flash all the way back to one of the first lectures we did, where we're talking about the average rate of change, and I let that delta, I let the distance between the point I was interested in and the other point I was using to get the secant line, I let them get smaller and smaller and smaller. You notice what? Remember what happened? Instead of blowing up and going to infinity like we kind of expected, that ratio settled down. It became a number, and that number we would ultimately call the limit and the instantaneous rate of change. We've got a very similar behavior going on here. As the number of intervals gets larger, instead of having the area blow up and become really big because we're adding together a really big number of rectangles, the area is kind of settling down. right? It didn't decrease nearly as much on the third try as it did on the first. We're going to use this 2 or 3 lectures down the road. We're going to use this combined with our new concept of an antiderivative to find a way to actually find the exact area under a curve. Okay, so but before we move on, right, I want to make one other point about this. I've been using the midpoints throughout here. There's nothing magical about the midpoints. You can actually choose any point from within these intervals. For example, let me clean up just a little bit here. Instead of using the midpoints, I could have used the left-hand endpoints. Right? What are the left-hand endpoints of the intervals? Well, the left-hand endpoint of the first interval is -2. Of the second interval, it's -1. The third interval, it's 0. And the fourth interval, it's +1. Well, I could have done the same thing. Instead, the area is f of -2 times 1 plus f of -1 times 1 plus f of 0 times 1 plus f of 1 times 1. All right, and got an approximation. Let's see if we can do this real quick. F of -2 is 0. That's the x-intercept. F of -1 is 3. F of 0 is 4. And f of 1 is also 3. So this is 0 plus 3 plus 4 plus 3. That's 10. It's even lower. It's making me think, I mean, we got an even better approximation that way. Right, so let's think for just a second about what these intervals would look like. Right, well, I'm going to use 1. Right, there's my first rectangle. So I went a little over here. And then I'm going to go to 0. And there's my second rectangle. And I went a little over there. But now look, at -1, there's my rectangle. I went a little under. Right? And now look, this next one is weird because the height is 0. It's actually kind of just this line here with an area of 0, if you will. So okay, here I actually had a fairly large overage. All right, so we're still not exact. Right? You see, there's still an error. It's still an approximation. Like I said, be a little patient. All right, and we'll see a way that we can eliminate those errors and get the exact values. All right, so before we do that, just brace yourself. We've got some technical language here we need to be familiar with, right? And all this is doing, for all it looks very wordy and technical, all this is doing is formalizing what we did on the last several slides, right? This is saying, suppose f is defined on a closed interval a, b. In my example, this was -2 to 2, which is divided into n subintervals. Okay, the first time we did this, n was 1, then we did 2, and then we went up to 4, of equal length, right? And we're going to call that length delta x. Remember, for us, it was what, 4, 2, and 1? Those were our lengths. Those would have been the delta x. xk star is any point on the kth subinterval. For the first 3 examples that we did, those were the midpoints. For the last example that we did, those were the left endpoints. So then this sum here, and I know this looks a little intimidating maybe, but look, all this is saying is take the functional value at every one of those points, midpoints, left side, whatever, multiply them by the width, and add them up. Right? That's all we did on the last several slides. This is just kind of writing it out in a technical way. Right? This special sum based on functions, rectangles, and so forth, it's got a name. It's called a Riemann sum. Riemann was a very famous German mathematician that did a lot of research and development in the early days of calculus. Now, we do have 3 special kinds. And again, this is just what we were talking about before. As a matter of fact, jump down and read the last one first. If these x sub k's are the midpoints of their intervals, then we call this a midpoint Riemann sum. If it's the right endpoints, then it's a right Riemann sum. If it's the left endpoint, then it's a left Riemann sum. mathematicians were not super creative in our naming. Okay, so it's these Riemann sums that we're going to look at, and what we're going to do. I'm looking ahead a little bit. I should skip ahead to, well, let's go ahead to the what's next slide. What happens is, if I take the limit of that Riemann sum as n goes to infinity, as we let the number of subdivisions get massively large, turns out that it doesn't blow up. Even though we're adding up an insanely large number of rectangles, it's still, a lot of the times, not guaranteed, but a lot of the time, it's going to come out to a finite sum, and that sum is going to be the area. Right? So that's kind of where we're going with this.